Okay, it's 10 a.m. Let's get started. And I apologize if I don't answer your question immediately. Because I'm using a third-party streaming tool, there might be a 20 to 40-second delay. So I will probably leave all the questions to the end if we have extra times. Okay. So hi everyone. This is Zefan from Singularity Engineering. So we are the ANSYS channel partner in San Francisco Bay Area. So we support full portfolio of ANSYS electromagnetic, fluid dynamic, and structural mechanic simulation tools. So today we are going to talk about RFID system simulation. So from here I will start talking about the antenna design. So as we may know, in RFID system there are two antennas. One is for the transponder and one is for the reader tag. So the design you are looking at right now is our transponder design. So as you can see, we in the tool here is our HFSS. So HFSS is a 3D electromagnetic simulation tool. You can see here we have our transponder antenna, and we have 2 feet to each side our antenna, and the pinky part here is the box. So this is the enclosure, and the green section is the dielectric. And on the left side we can see all the material properties. Okay, let me organize this a little bit. So here you can see we have our antenna surface is the copper, and also we have this part is the copper wire that excites our antenna. And for the enclosure, we have it as a plastic material. So this ensures that the enclosure doesn't affect our radiation pattern by a lot. So on the left hand side in our project manager, here is we have a few things that we need to set up for our antenna model. So the first thing, of course, is our excitation. So as you can see, I have 2 wave port for the antennas. So we set up 2 wave ports, and I have some boundaries. So one main thing for our antenna design is we always want to extract the radiation pattern. So in order to extract the radiation pattern, we need to set a radiation boundary. And if you are worried about the air box size for the radiation boundary, it's very simple. You just right click on the model, and then you can create an open region. And if you give your operating frequency, in this case it's 920 megahertz, and click OK, then you will just create a air box automatically. Okay, so next we have some perfect electric boundaries for the surrounding to the copper wire. Make sure there's no electric field escape from there, and make sure everything is going to the antenna. And next, here is I set up a mesh size for our antenna. You can always, if you are not working with a fairly large or fairly small system, you can just ignore your mesh unless you want to get a more accurate result. But with the default mesh, as HFSS can give you a very decent result already. So you don't have to set up the mesh all the time unless it's required. Next is we want to set up our solution setup. So here, basically, if you are if your antenna is only operates at one frequency, you can just set a single frequency at 920 megahertz, or you can do multiple frequency, or you can even do a broadband simulation. Okay, so and we can just leave all the others, and once we click OK, and I'm going to next is we are going to add a frequency sweep. So if you are interested in seeing the electric field, make sure you save your fields, and that's OK. Oh, one thing I forgot to mention is HFSS has ability, a real-time tuning capabilities. So in the setup, you can see we have the derivatives. So we call this the adjoint derivatives. This allows you to so let's say for one of the part, you can set up a parameter for, let's say, the radius of your antenna, or where you want to locate, where is the location for your antenna feed. You can set a parameter for that, and then you can check the box for doing the derivatives. And how the adjoint derivative works is, as we may know, the S parameter is related to the E field, and so when we run the simulation, HFSS will calculate the instantaneous slope of the E field, and then once the simulation is finished, the E field is the electric field is simulated, then we will get this slope for the E field. Then HFSS allow you to do a small change for your parameters, and by using that slope, we can see the small change for the S parameter as well. So I will show you the real-time tuning later, when we are looking at the results. So this is a simulated project, so I can just go ahead and look at the result. So one thing we care is the S parameter. So as we can see here is our return loss. So when we plot our results here, you can see the derivatives, and you can pick which one you want to tune for your S parameter. So if I select all, and then I just apply trace, then I will get this S parameter. Then I right click on result. I can do tune reports. So here you can see right now our radius of this is the radius of the antenna is 35 millimeter. So we can change it by plus 3.5 millimeter or minus 3.5 millimeter. And let's do that, see how the S parameter changes. So let's add a little bit more. Then we can see the S parameter changes a little bit more, but it doesn't look like, since the antenna is already tuned. So here I'm just showing you how the changes with tuning different parameters. So you just need to slide it, and once you find your desired results, you can just apply the offset to the nominal design. Then you will save this S parameter, and you will save all these parameters for your antenna. Okay, let's close that. So right now we have the return loss, and we have a decent result at 920 megahertz. So next thing we are going to talk about is the radiation pattern. So we can create two types of radiation pattern. One is the 3D polar plot, and the other one is just the cross-section radiation pattern. So let's take a look. we can overlay the radiation pattern to the design. So if we look at this, we have this radiation pattern for the antenna, and we can even overlay for the cross section. Let's double click this. Let's see how I should do this. Maybe I should just, okay, maybe not here, but yeah. But there's a way to overlay the the cross-section radiation pattern too, and the tune reports also apply to all the radiation patterns. So it probably doesn't. I guess this doesn't change the radiation pattern a lot. Okay, so next thing we are going to look at is the E field. So if we go back to our design, we can pick a plane. So if I want to look at the SY plane, so I can just choose the SY plane, go to fields, plot E fields. Okay. Then we can plot the E field for our antenna, and the E field the size of the field is only limited to the size of your air box. And later I will show you a bigger system for the RFID, so you can see a bigger E field. And I also plot the field for on the surface of the antenna and the dielectric. So sensing, you just need to select one of the face of the dielectric and the antenna and do the same steps. So here we have our E field. Okay, so this is for our transponder design. And next, I want to talk about the tag, the reader tag design. So here also we have an error box for the radiation boundaries. And I'm just going to hide this. Now, as you can see, we have a box. Inside the box, there's an object, and also on the top of the box, we can see there's a reader tag sitting there. So with the reader tag, we have an antenna. We have a strip line antenna here, a patch antenna here. So sorry if I called it a strip line antenna. Right, so here let's look at our tag design. So first thing, for the materials, so for the box, I'm just using a polystyrene foam. So we assume something inside this box is easy to break, so we are using the PS foam. So with this, I'm going to, so you can assign this thing to, like, let's say glass or anything. You can either do it as a metallic object or some like gases with high dielectric constants, and all of this stuff will affect the radiation pattern for our antenna. And so yeah, so the purpose here is show you how the radiation pattern would change with how the radiation pattern looks like with object inside these boxes, and what happens if we put the reader tag to the environment of like other objects. So here I'm for simulation purpose, I just choose this thing as a glass with relatively low dielectric constant. So the dielectric constant for this is around 2. So this wouldn't affect the radiation pattern of the antenna by a lot. But later I will put this thing in a metallic environment. So an environment with some other conductive metals, so then we can see how the radiation pattern change. But here we are just looking to see the very close to the ideal radiation pattern. So I will hide this. So here I have an enclosure. I will hide the enclosure. And here I have some copper for the antenna, and then we have the ground plane, we have the dielectric. So in this case, I'm going to set up the port. So this will excite our antenna. So for the solution setup, we have the same thing, like 920 megahertz. And in this case, I'm not going to do a derivatives. So instead of doing the derivatives, I'm going to do some parametric analysis. So I set out a few parameters. One is for the dielectric constant for our big box, the PS box. So the default dielectric constant is 1.04, but I'm going to vary a little bit by 0.03, and let's see how the radiation pattern changes. And I also changed the made changes to the objects. So one is we have the objects, and the other setup is we get rid of the object, and we can see how the radiation pattern changes. So we can set up parameter, we can set up the sweep, start from the size, and we can do the step. So next is, after we run the simulation, make sure you include the parametric. Make sure you enable the setup to include the parametric analysis. So this is with the default value. So with object inside the PS form and 1.04 dielectric constant for the PS form, and we can see like a very clear dipole close to the dipole radiation pattern. So okay. So next, we can also look at the cross section, and we can even look at the impedance. So next, I'm going to plot the different results. So right now, I'm going to get rid of the object inside of the PS form, and let's see how it changes. So now we have a more dipole-like radiation pattern. So let's look at that. Okay. And next is, let's change this a little bit more. I'm going to change the dielectric constant value for the PS form. So we were at 0.04, and let's do 1.07. Just a small change. Let's make it a little bit bigger. Okay. It doesn't look like there's a big changes with a very small change of dielectric constant, and that's pretty reasonable. Okay, so but I mean the purpose here is let you know that you can always change the dielectric constant value. You can even set up a few values that you want to test out to see the radiation pattern. And yeah, so this is a very simple setup, and that can show the capabilities of HFSS in antenna design. So next thing I'm going to do is I'm going to bring the transponder and the reader tags into a bigger environment, and let's see how the performance of them in the larger environment. Okay, so I'm going to just show another. So here, okay, we can see. So this is our RFID system. We have 1 transponder and 12 reader tags. Okay, so let's take a look of our setup. So here, same setup, so same material properties for our reader, our transponders, and we have this big box is our air box, the radiation boundary, and also for each of the boxes, the material for the boxes, the object inside, and the reader tags, everything is the same as the one we just saw. But the only difference is we are going to pile up 12 boxes together, and then we are going to orientate it in different direction. So also we are having one reader tag that is very attached at the bottom of the boxes, that is sitting on the metal plate. So we are putting all this on the metal cart, and let's look at the simulation. So same thing for the setup, and I have all the excitation for our tags and the transponders. So same parametric analysis. Now I have the So there's another thing is, right now we have so many excitations, right? But we can, after we run the simulation for all the excitations, you can pick the port that you want to look at the result and give it a magnitude to excite it. If you set it 0 watt, that means this port is disabled and it won't show the result for your plot and radiation pattern. So right now I'm looking at the wave port. So these two are excited. And this is for the reader tags. So let's look at the radiation pattern. So I'm going to again plot this in our modeler window. So right now we can see a very close to an ideal shape of the radiation pattern, but it still changes a little bit. It's not as round as the one we saw in an open area. So this is because we have some other objects in our environment. So the reader tags and the cart are about 2 meters away. So you can see the scale. So we can plot the radiation pattern for the bigger environment. We can also look at our E field. Okay, so next, let's look at the radiation pattern and how it looks like for the reader tag. So I'm going to edit the source, and I'm going to disable the transponder, and let's only look at the one that is sitting on the metal plate. The reader that I will point out was sitting on the metal plate, and let's see how it looks like. Okay, so it's very clear. So probably I need to adjust the location for the radiation pattern. Excuse me. So I just change the coordinate system, point it to our port 1. Okay, so we have our radiation pattern for this one here. So compared to the one we just looked at, this one is no longer a dipole radiation pattern, right? Because all the energy that is shooting to the metal plates get bounced off, and it's all the main lobe of the radiation pattern now is pointing up. So if we are moving the car too far away from our transponder, the transponder might miss this tag or not receiving the signal from this particular reader tag, and it might miscount one of the boxes. So the simulation here can help you visualize your radiation pattern and can help you optimize your design. Okay, so next is I'm going to do a second one. So we are going to do boxes that is in the middle and is a little bit away from our metal plate, and let's see how it looks like. So same thing, I'm just going to change the coordinate system a little bit, and I am going to excite this one. So that's our port 2, and apply. Okay, so now we can see this radiation pattern is very different from the previous one, right? So right now we have two main lobes pointing, or we have the main lobe pointing outwards instead of one particular direction, right? And this one has the higher chances that the transponder may read it, because it's not very close to the metal plate and all the energy are not bouncing upwards, right? So now we have this one, and we can also check out the E field and also the cross section for our radiation pattern. Yeah, so you can excite each single one and you can look at the results. So overall, HFSS is very helpful for you to design your antenna, and even in like a open space, or it's in a bigger environment with a lot of surrounding objects. Okay, so next is I'm going to talk about the more interesting part. So it's our circuit. So the circuit helps us to set up the full system for the transponder and the reader. So let me open up the design. So with the full system, it allows you to attach your circuit to the 3D model, and to go through all the process and excite your. Oops, probably I have to close this one. You can input your circuits to excite your antenna. So instead of putting an ideal source, you can input a more realistic RF signals. So okay, let's see. Okay, so here we can see we have our circuits. So in the middle part is our HFSS design. So this is the what's that called? This is the 3D model that linked to the circuit from HFSS design. So you can see we have 2 ports. So these 2 ports are for the transponder side, and this is connect to the transponder circuits. So on the right hand side we have 12 ports. These circuits are connected to 12 different reader tags. So here's this mod so here we have some .sp files. We have some S parameter files for different parts. So here we have the what's that called, the phase shifter. So the S parameter plot, and we have some S parameter file for the circulator, and here we have some S parameter for the backscatter modulator type of structure. Oh, sorry. So this is probably not the S parameter file. This is the spice netlist. So HFSS allows you to input the spice netlist, and so it supports HSpice, PSpice, spectral RF, etc. So you can import your spice netlist, or you can either import the S parameter file. Okay, so basically you just set up the file, set up the circuits, and link it to our 3D model to run the simulation. So because this model was created years ago, so I have lost the S-parameter file. So unfortunately, I cannot show you the result inside the simulator. But I can show you the PDF of the result that was recorded. So let's see. So let's look at our PDF. Present now. Okay, so we talk about the antenna design. So again, we want to highlight the adjoint derivative for real-time antenna tuning. So radiation pattern, we have the RFID tag. Okay, so here is our simulation of the entire RFID system. So by coupling the result in HFSS, from HFSS to circuit, and from circuit to HFSS. So here is an overview. We can set up the circuit. We can get a backscatter signal. We can detect all the possible signal, like input signal, demodulated signal, inside your circuit tree. And so HFSS and circuit is a two-way coupling. So you can bring your 3D you can bring your you can bring your 3D design result to a circuit. Then you can set up your circuit, run a simulation, and you can do the push excitation to couple the result from circuit back to HFSS by doing the push excitation. So instead of using using an ideal excitation source, you can use the source that was generated by your circuit, and with this source it will create the radiation pattern. Next, so this is a typical transponder circuit. So with the transponder circuit, on the top part, you can see we have some blocks. So we have the mixer, we have the RF amplifier, we have the circulator, we have the power divider, phase shifter, etc. And this is the ideal blocks that you can find in our circuit tool. So you can use the ideal components to look at the result, or you can replace the ideal component with the real circuits. So here we have each circuit correspond to each components. And so for circulator, instead of building a circuit, we just use an S parameter file. Or so either you can choose to build a circuit, or you can import a S parameter file or spice analysis. And if you design your circuit in the other tool, and this will save a lot of time too. And next, is we can detect the signals. So here we have the red is our input signal. We have the blue is a signal after our RF power amplifier. You can put a probe there like a voltage probe there to measure the signal at a certain stage. So here we can see two different signal after a 90-degree phase shifter. So next is our RFID tag circuit. So usually we have a backscatter modulator, we have the AM demodulator, we have our power generation and management, so like a voltage regulator, rectifier type of thing. So again, you can create the specific circuits, or you can use an ideal block, or you can import the spice analysis as parameter file. So this is a typical design that we have. So this is a charge pump, the rectifier, the charge pump design. So for the charge pump design, you can see this is there's a small block. Then if we expand this small block, you can see this is a charge pump that was built with transistors. So you can create this transistor in circuit, this transistor design in circuit, and then you can create a symbol for that, and you can place it in a bigger system. So you can do it this way, and you can also set up parameters, or you can set up optimizations. So to optimize your charge pump, you can you can locate your desired result. Let's say with different inductance. Excuse me. So you can set up the optimization for your charge pump as well. So next is our voltage regulator. So it's very straightforward. So once you set a voltage regulator, you can measure the voltage before and the voltage after to see the performance. So yeah, so next is our sorry, I didn't change the name, but this will be our backscatter modulator. So for the backscatter modulator, is this small part. So on the picture, on the circuit schematic here, you can see there are 4 transistors, and this 4 transistors form a buffer to drive the switch that turns the capacitor here on and off. So on the plot up here, the green curves in the plot are the RF signals. So this is, you can see it's very clearly to be modulated by the digital signal, so which is the blue curve. So again, we can do the transistor level design in our circuit, and you can do the optimization. And here is our overall test circuit response. So we have our RF input here, and we have our backscatter modulation, and on the top here, the cyan curve, you can see this is the RF's input signal to the tag. And these two, there are 2 zigzag signal. You can see is, let's see what it is. So RF modulated. So here we have the modulated signal here, and we have the other one is the signal after the charge pumps. Right, but this is a overall output plot for our circuit response with ideal RF input source. So I already showed this part. This is our full system field results with our transmit antennas. So okay, so I think up to here, I already conclude our circuit design, part for our simulations. So overall, we can do like just a antenna design for transmitting antenna, or we can just do like a reader tag antenna simulation, and we can do a full system transponder result with the circuit. So with the circuit, we can look at the result that without any tag is excited, or you can excite, let's say, one of the tag, and then you can look at the full system transponder results. Right. So next is how is the tag signal looks like at the transponder receiver input. So again, we have our RF signal and backscattering modulation signal. Okay, sorry if I have to change the title, but so this is our our full tag signals. So yeah, so after we have done let's say a medium environment, if we want a bigger environment, so we have 2 reader tag on both sides to make sure we read every. We have 2 transponder tag on both sides. Make sure we read all the reader tags on here. We can do it. Just put 2 transponders, and or you can make it like we have 2 door and you can set up like a fairly large environment for the simulation. Yep. So last but not least, I will highlight a few things to conclude our RFID system simulation today. So first thing is one of the most powerful things with ANSYS tool is we can combine HFSS and Circuit to design our full system, like full antenna system. So this will and HFSS and Circuit allows you to design, optimize, predict the performance of your RFID system, and in different scale of environment. So we also have the adjoint derivatives that supports the real-time tuning. So even this is for micro changes, but with the small change, you can see how you can improve your design. Let's say I increase my radius a little bit, and the S parameter is looking better than before. Then I know I need to tune my antenna radius to be bigger, etc. So adjoint derivative is one of the special capabilities that only ANSYS HFSS has, and you probably cannot find it in other EM simulation tool. And we also have this we also allow you to model multiple antennas in a single simulation. So in a single environment, so you can do a multiple antenna design in one simulation and plot different results. Yep. So again, if you don't like to create your circuit again, if you design other tools, you can always import the S parameter file, or you can even import the files from HSpice, PSpice, spectral RF, etc. And okay, next is you can do it in a fairly big environment, so you can narrow it down to a very small environment in millimeter range. So just the antenna itself, or you can model it in a bigger environment. Let's say mile, you want to set up a phone tower. So phone tower at on the top of a mountain, and then you want to see how your phone signals is like a few miles away. HFSS allows you to do this type of like extremely big environment simulation too. So another thing is you can also inject random noise source to your full system model. So right now the RF source we are using is ideal, but you are always welcome to inject a random noises to your system that you think might affect your radiation pattern or the performance of your design. You are welcome to do so. Yep. So the highlight will conclude our topic today. And yeah, so Oh, sorry, guys. So this video will be recorded on YouTube, uh, and it will be posted. So please let me know if you have other questions. If not, so I guess I will just stop here. Let's wait for a few minutes. Oh, another thing to mention is due to the quarantine situation, ANSYS has a special plan for um, our new customer or new user. If you are interested in ANSYS tool, feel free to reach out to me. We are happy to provide you some free trial license and you can play with the tools. So yeah, it looks like nobody has any questions, so I will stop here. In the future, if you have questions, feel free to comment below the YouTube or send me an email. Yep, thank you everyone for watching. Hope you all stay safe. Have a good day.